Definition 2.3. A subset A of a topological space X is called dense if its closure equals the entire set X. So its closure is as large as possible. Exercise 2.7. Let B be the set of all fractions of the form A over 2n, where A is an integer and n is a positive integer. Show that this set B is dense in the real numbers. Okay, well, by the definition above, we need to show that the closure of B is equal to R, right? So the closure is the intersection of all closed sets containing B. And if that's going to be R, then R must be the only closed set containing B. Right? So we show that the only closed set containing B is R itself. All right, well, we eventually want to get to open sets, right, so that we can work with the basis for the topology R. So we can say that equivalently, an open set of the complement of B must be empty. Right? Why is that? Well, let's see, an open set of the complement, if you look at its complement, that would be a closed set containing B. And it would have to be R, right? Therefore, that original set would be empty. Okay, so those two things are equivalent to one another. So, good. So that's what we need to show. So let's suppose, for contradiction, but that's not true. Namely, we have some U contained in the complement of B, which is open and non-empty. Okay? We need to get a contradiction out of that somehow. Well, now that we have an open set, we can make reference to the basis of R. Right? So by the definition of the standard topology on the real numbers, which is the one we're using here, this open set U contains some basis element and some open interval from C to D, right, for a pair of real numbers C and D. Well, we are going to show that this open interval from C to D contains at least one element of B. Okay, so its intersection with B is non-empty, and that's going to contradict the assumption that we've made up here that U is in the complement of B, right? Another way to write that would be that U intersect with B itself is the empty set. Okay. So why is that? Well, if the interval from C to D intersects B, that interval is contained in U, right? So then U intersects B in at least the same places that CD does. Okay. So all we need to do to finish off is to show that this intersection is non-empty, right? To find at least one element in the set B, at least one of these fractions, which is between C and D. All right, well, here's how we're going to do that. First of all, we're going to let n be some positive integer, which is so big that 1 over 2 to the n is less than the length of this interval, right? The difference between its two endpoints. Okay. And let me try and draw a picture to illustrate what we're up to here. Okay. So we have our real number line, and we have an interval from C up to D. And trying to get 1 over 2 to the n less than the length between these, so that as multiples of 1 over 2n sort of march in this general direction, maybe this is one of them, and then maybe the next one is here, and the next one would be about here. And the idea is that if the distance between these multiples is small enough, less than the distance from C to D, then there's no way that these multiples are going to kind of jump over this interval. Right? One of them is going to have to be between C and D, and that will be precisely the a over 2 to the n that we're looking for. Okay. So what we have to do now is figure out what the a should be, and the way to do that is to redraw this picture, but to stretch the whole thing out by a factor of 2 to the n. Okay, so just multiply all the numbers by 2 to the n. So this number here is 2 to the n c. This one is 2 to the n d. And then we're just going to let a be well, what we think is between these, but all we can say out front is that it's going to be the least positive integer, which is greater than this 2 to the n c. Okay, and then we need to make sure that we end up with an a over 2 to the n between c and d out of that somehow. So let's see if we can get the inequalities to work out here. Let me write down what I said. Let a be the least integer greater than 2 to the n times c. Okay. Well, then I guess that means that if you subtract 1 from it, you still have an integer, but that one must not be greater than 2 to the n c, right? So a minus 1 must be less than or equal to 2 to the n c, right? Or else a wouldn't be the least such integer. And okay, and we know that that's less than a by choice. Okay. Well, we want to look at each sort of inequality here separately and figure out what it says about a over 2 to the n. Okay, so if you take the sort of right-hand inequality here and divide both sides by 2 to the n, you get that c is less than a over 2 to the n, which is great. That's half of what we need, right? We also need to show that a over 2 to the n is less than d. Okay. All right, so, well, also, if I look at the left inequality here, and I solve for a, I get that a is less than or equal to 2 to the n c plus 1. And now I can divide that through by 2 to the n, because what I really want to know about is a over 2 to the n. It's not a 2, a over 2 to the n. And okay, so that's less than or equal to c plus 1 over 2 to the n. And all right, well, here's where we use that 1 over 2 to the n is less than d minus c, right? So this is less than what I get if I replace 1 over 2 to the n by d minus c. But that's just d, right? So putting all that together, we get that a over 2 to the n is less than d. Okay. So we have that a over 2 to the n is greater than c and less than d, and hence we have found an element of b which is contained in the interval from c to d. So this interval has an intersection with b which is not empty, right? It contains at least this one element, not equal to the empty set. Okay. And that's what we needed to show in order for our proof by contradiction to work out. So there you have it. This set B is dense in the real numbers.